Imagine you are looking at a beautiful view of Cornell out of the window. Maybe you want to look at the buildings or how many cars drive by, or if it might rain soon. The only issue is the window's very smudged, so even though the view is all there, the information you might be looking for is a little difficult to see. Well, this is similar to what happens to the data taken at the FAST or Forming and Shaping Technology beamline here at the Cornell High Energy Synchrotron Source. At FAST, we use X-rays to study how structural materials such as metals, ceramics, and cements react when we crack them, pull them, or compress them, for example. This gives us information about how and why certain materials may fail. To put it simply, beams from a synchrotron go through an undulator, which produces X-rays. The X-rays go through a monochromator, which allows the user to select what beam energy they want. Internal features in this monochromator is what causes striations in the resulting images of the sample. Here are some images to show what I mean. On the top is some slower data taken at an exposure time of 1 second, and on the bottom is some fast data taken at an exposure time of 200 nanoseconds. In both images, we see these horizontal lines that do not belong. Also notice that in the high-speed data, there is a lot of annoying graininess. My project this summer was to answer the question, what can I do to clean up these images so I can get a clear view of the sample without those pesky artifacts smudging up the data like smudges on a window? Well, the first idea was to use a technique called bright field correction. In this method, I used dark fields and bright fields and did some math with them, hoping that if I could normalize my sample data with them, it will reduce the noise. Here, a dark field image is an image taken without the beam and without the sample, while a bright field image is an image taken with the beam but with no sample. The second method, and the coolest in my opinion, was called frequency domain filtering. With this technique, I did what is called a fast Fourier transform to each image. This gives us back a spectrum that plots all of the frequencies in the image. The cool thing here is that vertical lines in the spectrum correspond to horizontal lines in the image, and horizontal lines in the spectrum correspond to vertical lines in the image. With that knowledge, we could guess that if we masked out frequencies in the spectrum related to those horizontal lines and reconstructed the image, the striations would be reduced. So here are some results for the slower data. The two most important things I look for in these corrections is if the striations were reduced and if the sample still remained clear. In this case of the lower speed data, both of these criteria were met using both methods, which is a success. Here are some corrections run on the high-speed data. These images show a sample of glass as a crack forms in it. On the left are images without any corrections. In the middle is the data after a bright field correction. With this correction, it is difficult to see that the glass is even moving at all, so it fails the clear sample test. As far as the striations go, it may have helped reduce them a little bit, but not a whole lot. So for the high-speed dynamic data, bright field correction seems to fail. On the right, we see the images after a frequency domain filtering. Now these results look promising. Not only have the striations been greatly reduced, but the sample edges also remain clear. I consider this a success. So what's my conclusion? From the work I did this summer, I can say that bright field corrections may work okay for low-speed images, but doesn't seem to work so well for the high-speed images. However, frequency domain filtering works well for clearing up both of our